All right, 8.2, we are going to estimate a population proportion. So we're going to take this idea of confidence intervals and extend them to our knowledge of population proportions. We're going to look at how to determine the sample size and describe how the margin of error changes with the sample size and confidence level. So just to talk about an activity that would let us create a confidence interval, we have this container full of different beads. Our goal is to estimate the proportion of red beans in the container. And we could go through this process. We could form groups of 3 or 4. We could take a cup to make a simple random sample. That is, dip the cup into the large bin full of beads and collect a simple random sample. The point estimate would be you count the number of red beads and divide by how many beads you had total in your sample. We're going to find a 90% confidence interval for this parameter p. So let's walk through this process. So suppose we collect a simple random sample where we have 107 red ones and 144 beads total. Our p hat, our point estimate for p, would be 0.426. If the sample size is large enough, that is, if NP and N1 minus P are at least 10, the sampling distribution for p hat would be approximately normal. And the mean of that sampling distribution of p hat would be p. This is stuff from the previous unit on sampling distributions. And we have this formula for sigma p hat, that's p times 1 minus p over n square rooted. And we have this normal distribution. We have the mean in the middle. We have our standard deviation. And we can use this to calculate percentages. Cool. But we don't know p. If we did, we wouldn't need a confidence interval. In large samples, p hat will be close to p. So we're going to approximate this normal condition and approximate the standard deviation calculation by using p hat instead of p in these formulas. So in practice, these are the conditions for constructing a confidence interval for a proportion. First, we make sure that we have a simple random sample. Yes, we did that. We're getting our point estimate. When we're checking our normal condition, we're going to use n times p hat and n times 1 minus p hat. Those are both greater than or equal to 10. Independent, well, we're sampling without replacement, so we need to check our 10% condition, and our population is more than 10 times this. So if I told you that there were 3,000 beads in the container, our independence is satisfied. We can use our standard deviation calculation. So since these three things are met, it's safe to make our interval. So we have this formula. Statistic plus or minus critical value times standard deviation. We're using our p hat to estimate p, and since we're independent, since our 10% condition is met, we're actually calculating the standard error. When we substitute p hat for p, we are now finding the standard error instead of the standard deviation. Slight difference in terminology, same thing that we're doing though. So when the standard deviation is estimated from the data, the result is called the standard error of the statistic. If the normal condition is met, we can use the normal curve. To find a confidence interval, we need to catch the central area C under the standard normal curve. So 95%, if we're finding the 95%, we can use a critical value of 2, but using table A or the calculator, we get a more accurate value, more accurate critical value. What we find is that the z-score is actually 1.96 for a 95% confidence interval. Remember, we're only using this normal curve because our normal condition was met, n times p hat and n times 1 minus p hat. So we call this z star. This z star is going to represent our z-score, our critical value for our confidence level. Here we want a confidence level for 80%, a confidence interval for 80%. We're going to assume the normal conditions met. We want z star. So central 80%, that means our two tails, these two are both 0.1. we can search table A to find the area where 0.1 is still left. So we're looking in the body of the table, and we're trying to find the percentage that's as close to 0.1 as possible, and that would be right one of these two. And the closer one is the 0.1003, and that z-score would be negative 1.28. There's our critical value. Our critical value is z star equals 1.28 for an 80% confidence interval. A one-sample z-interval for a population proportion. So this is our confidence interval for p. Once we find our critical value, our z star, we're going to multiply by our standard error, our standard deviation, and add and subtract it from p hat. So here is the process that we will go through. Notice that we can only use this interval if the successes and failures are both at least 10, and the population is at least 10 times as large as the sample. In other words, our normal condition must be met, that's this first part, and our standard deviation can only be calculated if we're finding our 10% condition to be true. So, back to our beads. Calculate and interpret a 90% confidence interval for the proportion of red beads in the container. I'm going to claim that 50% of them are red. Let's see if you believe me. So our sample proportion, our p hat, was 0.426. We checked a little bit ago that we're independent, that our 10% condition is met. We saw that a few slides ago. So we can calculate our standard deviation, and we checked that our normal approximation was good, NP and N1 minus P, substituting the p hat, of course. So our normal condition works. So we're using our table. 90% confidence level. Our z star would be 1.645. It's actually halfway in between these. 90% confidence level means the two tails of our normal distribution would be 0.05 and 0.05. That's exactly halfway in between these two areas. So we could say that our z star is 1.645. So statistic plus or minus critical value times standard deviation. Here's our formula, standard error. So 0.426, that's our p hat. 1 minus 0.426 divided by 251, that was n. Here's our critical value. There's our point statistic, or point estimate. There's our margin of error, 0.051. We add that and subtract it to our point estimate. We get this interval. So we're 90% confident that the interval from 0.375 to 0.477 captures the actual proportion of red beads in the container. So do you believe me? Do you believe me that it's 0.5? I would say probably not. You should doubt the claim. This interval gives us plausible or possible values for p, and 0.5 is not contained in the interval. So I'd say maybe I'm lying. Maybe I don't really know what I'm talking about. Maybe it's not really 0.5 and I'm just guessing, or just trying to see if you understand how to make a confidence interval. So making our confidence interval, we can relate this to the 4-step process. Step 1, state what parameter do we want to estimate and what confidence level. So I want the proportion at a 90% confidence level, for instance. Plan, identify an appropriate inference method. We're going to check the conditions. That is, we're going to check the normal condition. We're going to check the 10% condition. If those conditions are met, we're going to perform the calculations. And then we conclude, we interpret our interval in the context of the problem. And that's what we ended with right here. This was the interpretation. This was the state part. So you should be able to identify each of these 4 steps in the previous problem that we just got done doing. And you should have written this problem out. And why don't you go back right now and identify each one of these 4 in that problem you did. Now, choosing the sample size. in planning a study, we need to choose an appropriate sample size. And we want to estimate the population's proportion within a given margin of error. So margin of error, ME, is Z star times our sampling error. And Z star is contingent on or dependent on the level of confidence. Because the margin of error involves the sample proportion p hat, we have to guess the value when choosing n. There are two ways to guess p hat, because we don't know p hat, not until we do the study. So we can guess p hat based on past experience or a pilot study, or we could use p hat equals 0.5, because the largest that the margin of error will ever be is if the p hat is 0.5. So to determine our sample size that will yield a confidence level of C for a population proportion with a maximum margin of error, we solve this inequality. The margin of error will always be less than or equal to the margin of error if we guess p hat to be 0.5. So we have to guess p hat, remember. We don't know p hat until we collect a sample. We're trying to determine how big the sample should be. That's why we guess. It's an educated guess, though. So let's do an example. It says read the example. Well, we're going to just look at this. Determine the sample size needed to estimate p within 0.03 with a 95% confidence. I'm not even going to tell you the context for this problem because it doesn't really matter. So 95% confidence, that means our Z star, our critical value, is 1.96. So 1.96 times our standard error has to be less than or equal to 0.03. If we multiply both sides by the square root of n and then divide both sides by 0.03, we get this inequality. And worst case scenario for the margin of error will be when p hat is 0.5. So n is going to be greater than or equal to what we get from this calculation. And since we don't know p hat, we have no clue what it is. Worst case scenario, biggest sample we could possibly need is when p hat is 0.5. We put that in, we crunch our numbers, and we get that n is greater than 1067.11. So as long as we sample groups of 1068, no matter what the sample proportion is, our margin of error will never be more than 0.03 at 95% confidence. So what's going on here? This is what we looked at in this section. Make sure you look at these and make sure that you're identifying where we talked about this a couple minutes ago. Four-step process, margin of error. And in the next section, we will look at how to do this for the population mean. And there we have it. We're stopping now. If you have questions, make sure that you ask.